So normally I do a different style of video. I usually present it to you with a much more edited and more focused way, but I'm going to try something different, and I'm going to try and do a past paper. This is the Specimen past paper for statistics, the GCSE statistics course for EdXL. It's the higher paper 1, and I'm basically just going to try and answer it as if I was a student taking the exam. Now it's been a whole year since I last took GCSE statistics, so do forgive me if I make mistakes, and please do give me feedback on how exactly I do, because yeah, I don't really do this often, and this is much more different from my edited approach, where yeah, I filter out a lot of my thoughts. So I will be having a mark scheme with me as I do the questions to make sure I'm not giving any false information, but I'm going to try and give my initial thought and then cross-examine it and reference with the mark scheme to make sure I'm correct, and yeah, it will influence how I answer the questions, but I'm going to try and give an insight into how I would approach the questions, so hopefully it will still be some use to you. And if you need it, here are the formula that you're given. Now, the formula that you need to remember, there is a list. I'll try and put it in the description if I have time. It's a longer one than this, but again, most of them you can derive them, and it's not too hard to memorize. More about intuition, and yeah. So let's do question 1. In the first question, we're told that the Venn diagram shows us information about 20 films shown in the UK in 2015. A is the event that the film was produced in the UK, and B is the event that the film made more than £40 million. The numbers in the Venn diagram indicate the number of films. We're told to explain fully what the number 3 represents in the Venn diagram. So 3 is in this section here, this little, it's literally called the intersection point. And the intersection point, basically, if you don't know your Venn diagram notation, well, I'd suggest revising it, but it's A intersects B, and that's the intersection point. Now, this means basically A and B. So A is the event that the film was produced in the UK, and B is the event that the film made more than £40 million. So if we're looking at the intersection of A and B, then we can see that this means it was produced in the UK and it made more than £40 million. So I'll write this. We're told to find the probability of B. Now, I don't want to overcomplicate this, but we need to look at the context because that will help us understand it. B is the event that the film made more than £40 million. Well, you're just asking the probability of B is that out of all the 20 films that were made, because it says 20 up here, how many are in B? Or what is the probability of B, which is how many of them were made with the set B in mind, which is the event that they made more than £40 million. Well, you can see that this is 3 plus 2. So it's going to be 5 over 20. That's going to be our answer here. For part C, the probability of B, and then this line, A. This firstly, we can write this as, this means given. Now, you read it as B given A, and this means that given this happened in A, what's the probability that will happen in B? Now, there are some formulas you need to know, however, it's not really necessary and you can derive them on your own, but I'll just write them out here. So, the probability that B given A is equal to the probability of the intersection of A and B over the probability A. And you can kind of visualize this in a graph. You're going to find the probability of A, which is everything in this part here, and then you're going to find everything within that part, which is also in B. So this part here. What you end up with is, if you just find the intersection of A and B, and we've already got the intersection is 3, we just need to find the probability of this. So the probability of intersecting A and B is 3, and the total number is again 20, as we've seen from the top. So we'd have 3 over 20 and then we'd have to divide it by the probability of it happening in A. The probability of A happening is 5 plus 3 out of 20, so 8 over 20. If you just type this into your calculator, there's no need for you to do this in your head, because in the exam you're going to be under high pressure and you're just going to make mistakes, so it just gives you 3 over A, which would be our answer. Now how would you be able to find this out using some intuition? So it reads B given A. Now it's kind of self-explanatory. Once you get it, it just clicks. So given A means that it has to be in this circle A, and the probability that happens in A and B, well, it's only this one. Only 3 happens within A and B, which is the intersection, and only 8 happen in just A. And that basically gives you your 3 out of the 3 plus 5, which is 8. However, this is a more soundproof method. It's more likely to get you the marks because it's showing you're using the formulas. Using your answers to part B and part C, explain whether or not A and B are independent events. Now this is going to use some pre-existing knowledge. You've got to know this or you're not going to be able to really answer this question. So the probability that B given A, as we know, is 5 or 3 over 8. Now, if they're independent, and if they were, this means that A does not affect B, and B does not affect A. That's as simple as it gets. Now, if that was true, the probability of B should just be equal to the probability of B given A, and the probability of B is 5 over 20. Now you're saying that if they're independent, A doesn't really affect it at all. A is kind of just, well, it's just redundant here. So if they were equal to each other, then we could say that the probability of B given A, as is equal to the probability of B, then they must be independent, because A clearly has no effect here. But if you look at it, 3 over 8 is not equal to 5 over 20. In fact, this means that they can't be independent. And this is basically the reasoning you have to give, is that the probability of B given A is not equal to the probability of B. So what you'd write is that 3 over 8 is not equal to 5 over 20, so they are not independent. This was kind of difficult, well, mostly part D. However, if you found the first couple of parts kind of hard, I'd recommend that you'd revise Venn diagrams and probabilities, because, well, it's not really high in marks, it's still an important topic, and obviously if you don't get it with the exams this close, you should probably be revising this. Now, that's the end of this question, for question 1. We'll move on to question 2 now. There are 11,727 students at a university. Their nationality is classified as either UK, EU, or international. The table shows information about the nationality of these students. And here's the table. The manager of a bookshop wants to carry out a survey into the books read by students at this university. She is going to take a sample of 600 of these students. The manager plans to sample 200 UK students, 200 EU students, and 200 international students. Write down the name of this method of sampling. Now, instantly, without even looking, 2 things come to my mind, because I'm seeing the exact same number. Now, it could be stratified sampling, or it could be quota. But here's a key clarification. Stratified sampling is when you do it by proportion. So for example, here there's much more UK students than international students, because, well, you can clearly see there's roughly around 8 times more. However, you're going to use the same number of students for each. That's clearly not proportional, whereas quota is where you use the fixed quota. You use a fixed number of students or whatever you want to test per group. So this is going to be quota sampling. Now, give a reason why this method might not be appropriate. Well, just like I said, if you're in the UK and there's only 200 of you being selected out of all of your fellow students, and you see that 200 are also being selected out of EU or international, you're going to be quite annoyed if you wanted to go to the bookshop, because you've got less chance of being in, and therefore it's not representative. Looking at the mark scheme, you could also put that it's not random or it's possibly biased. For part C, a shop assistant suggests that it would be better to select a sample of 600 students and then stratify by nationality. Work out how many EU students there should be in this sample. I'm just going to state the formula. You don't have to, but it just helps me when I remember it. So the strata over the population, or the total, multiplied by the sample size. And this should give us the number of EU students that should be in the sample. So if we look at the EU students, that's this one here, we get 979. That's our strata. And then the total, the question says here and says here that it's 11,727. And then we use our sample size, which is given by the question again, which is 600. So we need to put this into the calculator. Now feel free to just put this in. So I've typed that into the calculator, and what I've got is 50.08 and so on. And since we're talking about students, i.e. whole numbers, we're going to just round it to the nearest integer, so 50 students should be in our sample. Part D says that 3 students, Amy, Beth and Carlos, bought the same 8 books from the bookshop. The manager asked Amy, Beth and Carlos to rank these 8 books in order of how much they enjoyed them, increasing order, sorry. The manager calculated the Spearman's rank correlation coefficient for the ranks given by Amy and Beth. She got a result of 1.2. Explain how you know that this result is not correct. If you do Spearman's rank calculations, and you would have to do them, you will know that you will never get an answer between -1 and 1. Because simply Spearman's rank measures how strong or weak rank correlation is. So if you see a value outside 1.2, this can't be correct. Just like you know that probability cannot be outside the range of 0 and 1, Spearman's rank is similar in the fact that it cannot be outside -1 and 1. And you can see that 1.2 is greater than 1. So the result cannot be correct. In the exam, I'd possibly make this a bit more worded, and I'll say that Spearman's rank correlation coefficient can only take these values, -1 and 1, and then I'd show that 1.2 is greater than 1. However, this should be sufficient. The manager also calculated the Spearman's rank correlation coefficient for the ranks given by Beth and Carlos. She got a result of 0.74. What type of correlation is shown by this result? Since the whole thing seems to be 2 marks, I'll just write positive, but sometimes you might need to be more specific and give, well, an adjective, either strong, weak, moderate. Interpret this result. Well, a positive correlation can be kind of seen like this, like that, and it basically suggests that as the rank of one goes up, the rank of the other goes up. So they basically have similar ranks, and they're basically ranking books here, if I'm not wrong, and they're ranking their books in increase in order. So if they're ranking books kind of similarly, we could say that Beth and Carlos agree, and then probably reasonably, with each other. So the table shows a summary of the results of a long jump competition. The distance jumped is shown here, the frequency in the next column. We need to find an estimate of the mean distance jumped. You may use the extra columns in the table. The first instant thing that comes to me is the word estimate. This is a keyword, to be honest, so we need to find an estimate of the mean. Now you should probably be familiar with this formula. You don't have to be, and I'm just going to write it for the sake of it because I think it's a useful thing to know, is that the mean, which is x bar, is equal to the sum of the midpoint multiplied by each frequency over the sum of the frequencies, and this is just sigma, which is equal to the sum. So they've given us 2 extra columns. How nice of them. So we'll just use them, and it's up to you what you want to use them for, but to me it makes sense to find the midpoint. So like so, and I'll still label this x, to be honest, and then this should be the midpoint times x, which I'll just call f of x. Now when you look at the midpoint, what is it exactly? Well, it's the midpoint between each of the intervals. So 7.1 and 7.3, you can clearly see here that is 7.2. Now how would you do it for a more complex one? Well, you just do 7.1 plus 7.3 and you'd find the mean. That would give you 7.2. So I'm just going to write them all down quickly now. Now I've done that, f of x is literally equal to f multiplied by x. So using your calculator, well, you can have a go right now, type these all in and write their respective values in. Okay, so I've got my values now, and I'm going to just write them in. So you should get, for the first one is 7.2, then you should get 14.8, then you should get 38, 70.2, 64, and 24.6. Now you've got a sum of x times f, or f times x. I've written it the wrong way around here, or the other way around. There's no right or wrong. I'll just sum them up, which is what this means. So I'm just going to use the formula and find the sum of all of these. So I'll do 7.2 plus 14.8 plus 38 plus 70.2 and so on. And go ahead and type this into your calculator. And one more thing, some of the frequencies, probably should have done this first. And 1 plus 2 plus 5 plus 9 plus 8 plus 3. So for the numerator, I just calculated this now and I got 218.8, and used the calculator to find the sum of the frequencies. And as always, don't do these in your head. You've got the calculator for a reason, you might as well use it. You should get 28. So 218.8 divided by 28, sorry. And that gives us 7.8142857. And does it tell us what to round it to? I don't think it's a big topic of what you should round it to, but seeing as most of the values given are to 2 significant figures, I'll just stay with that, and I'll keep it at that. And the 2 significant figures, this would be 7.8 meters. And yeah, remember to give units. They've given it for this question. However, it's a good habit to get into. So you should have 7.8 meters as your answer. For part B, we're told to draw a frequency polygon for the data. So let's highlight our keyword, and here it's frequency polygon. Now a frequency polygon, the idea is that at each frequency you draw the frequency matching to the midpoint of that interval. Sounds confusing, but let's just do it and it should make a bit more sense. So we need to first look at the graph they've given us, and they've given us the horizontal axis, but they've not given us the vertical axis labels or anything like that. So that's probably going to be what we need to do. So on the vertical axis, we're probably going to want to put frequency. Now let's go back to the table where we see that the highest frequency is this value here, 9. So with that in mind, what would be the best scale to use? If there are 10 squares, then it's probably better to increment by 1 and go up to 10, which would kind of accommodate all of the different values that we have for our frequencies. So I'm going to go in ones. So now we've done the axis and the labels, we now need to focus on the actual frequency polygon itself. So at each midpoint, and the midpoints we have, we've labelled them all 7.2 through to 8.2, then we need to plot the corresponding frequency. So at 7.2, which is our x value, we need to go to the frequency which matches it, and that's 1. So I'm going to plot that here. Now we go to 7.4, and we have 2. For 7.6, we have 5. For 7.8, it's 9, which is our highest value. Now for 8, it was 8. And for 8.2, it was 3. Okay, now the important thing I need to mention now is that you always connect the midpoints to each other using straight lines, which is why I've got my ruler. It's going to be interesting how we use this. Yeah, there's not much more to it other than you just join them in straight lines and make sure the midpoints are touching, to be honest. That's all I can offer. Okay, kind of messed that one up. That's kind of good enough. You should, with more accuracy, with a paper and pen, hopefully do better. And I recommend doing it in pencil and then tracing over afterwards, because you don't want to make a mistake in the exam, do you? So part C asks us to describe any skew, if there is any, shown by the data. Now this is another thing that you must know, so I'll just draw quickly 3 different types. What you see here are 3 different types. This is negative skew. This is symmetrical or no skew. And this is positive skew. Now, it kind of goes against what you'd expect. The one with a almost positive gradient is negative, and the one with an almost negative gradient is positive in terms of skew. And it's kind of confusing when you first look at it, but over time, as you do more questions, you just get used to it. And so you just have to think of it as almost opposites to each other. And that's what I do. And you can see with here, the general shape, it kind of follows an upward sloping, like so. And that kind of matches this graph here. So we can kind of say it's a negative skew. So yeah, that is what I'm going to put a negative skew. Question 4. The pie charts show information about the departure country of the overseas visitors to the UK in January and July of 2016. Based on the 2 pie charts, Royal makes these 2 conclusions: that there are more visitors from Europe than from North America in both months, and that there are more visitors from Europe in January than in July. Assess the validity of each of his conclusions. Let's focus on one first. There are more visitors from Europe than from North America in both months. So North America is the slightly darker shade than Europe, and we can see that Europe has a larger share of each circle than North America, so it represents a higher proportion. So the claim that there's more visitors from Europe in both months is true, even if the size is different, which might come on to later, as long as the proportions are different within the same one, we can confidently say that there are more people coming to Europe, or going to Europe, whatever the context, than in North America. So I'm going to put that Rawls' claim here is valid due to Europe. Oh, terrible spelling. Having a higher proportion than North America. In both months. For part 2, or the second one, he says that there are more visitors from Europe in January than in July. Well, look, there's no numbers here given to us. We're just given the dates and nothing else. So it's actually impossible to say. So to be safe, you meant to say that it's invalid because, well, the size here, they're not comparative pie charts, which ironically the next part is about. However, you can't assume that here, and so therefore we don't know if there were actually more in January than in July. So we'd put invalid, and then literally the answer that I gave is that they show proportions rather than the actual numbers of visitors. Now Judith decides to replace the pie charts with comparative pie charts. Explain how comparative pie charts are more appropriate than pie charts to compare the number of visitors in each month. But one thing that you naturally expect is that the exact same number of people will not be going overseas in the same month, different months, So you're not going to have exactly 10,001 in both months. You might have a slight variation, maybe a lot of variation. Either way, they're not going to be the exact same. We can write that comparing the areas would effectively compare the numbers. Part C now. The total number of overseas visitors to the UK in January 2016 was 2,599,000. The total number of overseas visitors in July of 2016 was 3,786,000. Judith's comparative pie chart for January 2016 has radius 3 centimeters. Calculate the radius of her comparative pie chart for July 2016, giving my answer to one decimal place. So this is going to utilize another formula. Now you don't have to use a formula, there is another method and it kind of derives this formula, and you can think about it using intuition if you like, but in the exam you're just going to want to plug in the formula, and that's what I'm going to do here. I'm going to give you the formula. So the formula is the square root of f2 over f1 is equal to r2 over r1. Now what does exactly all of these mean? So f2 is the second frequency, f1 is the first frequency, r2 is the second radius, and r1 is the first radius. Now look at the question and just see what information you've been given, and just look for the numbers. Here we can see this, this, and this. They just stand out to me. They don't particularly mean anything at this point in time. But you can see that this and this, the top and the bottom pieces of information, they link. They're both for January 2016, and you can kind of see that they link together. If the radius is 3 for January 2016 and July 2016 has a higher population, well, the previous question just indicated that we use the areas to compare the numbers, so the radius naturally should be different, and we're going to basically link the radius using these. It's kind of complicated. I'm going to try and just do the question and it should make more sense. The best thing to do here would be to assign each of these. So for January 2016, we have 2599000, and also the radius is 3 centimeters. For July 2016, we have the following number, and we don't know the radius, so the radius is unknown. You can go with whatever you like, but the general thing I go for is to assign R1 and F1 to the one that you have information for both parts, which is here, January 2016. We have information for the radius and information for the frequency, so I can assign these the values of F1 and R1. You don't have to give it this, but it makes it much easier in my opinion. So therefore, for July 2016, it would be R2, and for July 2016, the frequency would be F2. Now using this formula, we just have to plug and go from here. So the square root of F2 over F1. F2, as we know, is 3,786,000 all over 2,599,000. And this is equal to the second radius, which we don't know, over the first radius, which is 3. And you can see that I've kind of used all of this information here. I'm going to move it to the side. And so now we can kind of use this in order to help us find R2, which will be the radius of July 2016. So it's just a bit of rearrangement here. I'm going to bring it to this space here so it's much easier to see. So R2 should equal, and if you've imagined this bit is dividing, you're multiplying by the 3 in order to eliminate it. So we'd have 3 lots of the square root of all of this. And then you just have to type this into your calculator. And what you end up getting is this following. The question tells us to give our answer to 1 decimal place, and so doing this, we need to put this to 1 decimal place, which is equal to 3.6 centimeters. This question is quite a big one, and my only advice here is to keep practicing these types because honestly, this is the only way you can get better at it. So a database contains information about the 2,567 people registered at the medical center. Here is the information that the database contains on each person: the name, date of registration, etc., etc. Now you should notice that they've given this for a reason. It's just not random information to throw you off. They've given it for a specific reason. So Rebecca wants to see if there's a relationship between the age of a person registered at the medical center and the number of appointments this person has had at the medical center. Describe how Rebecca can plan to use technology to help her process and present the data for this investigation. You should refer to the advantages of using technology to process data compared to doing so by hand. And this is a key piece of information that you really need to know. So refer to advantages using technology compared to by hand. And then another thing is you can split this into describing how Rebecca can plan to use technology and the advantages of using technology. So advantages and planning to use technology. So there's kind of 2 pieces of your answer that should be, so there should be the plans to use it and what you can actually do with the technology and the advantages of doing so. And basically, because it's 6 marks, you're going to want to go for a rough 50-50 split. So you can do 3 general points per heading. So if we look at the planning, what can we do with this data? Well, we know that there's 2,567 people, which is a lot. And Rebecca's aim is to see if there's a relationship between the age of a person and the number of appointments. So she's going to have to select people, right? So how can she do this? Well, we can use simple random sampling. If you don't know what that is, please do revise that. I've got a video on that. After assigning people a number, you need to generate random numbers. And this is something that technology is great at doing, because other than doing it with a hat, there isn't really any other alternative other than technology. So we can write that it generates random numbers. Now, the last bullet point here makes this more focused. You should refer to the advantages of using technology compared to doing so by hand. So compared to doing this by hand, and let's just say for the sake of it that we're using a hat instead of a random number generator, what's the main advantage here? The first thing that comes out to me is that it saves us time. So it saves time. And that makes sense because technology is meant to automate the process and make it a bit more quick. So that's basically a point and an advantage to go with it. So the next one we can think about is, well, look at all this information given. She just wants to know about the age of the person and the number of appointments. So all of this here, the name, the date of registration, the phone number, etc., this is all irrelevant information. So we can kind of say that the technology will remove irrelevant information and what does this make? What's the advantage here? Well, it makes it easier to read the data, and as a result of being able to read the data and therefore correct mistakes. So that's another plan of using technology, removing irrelevant data, and an advantage to go with it. So that's kind of 4 points there, which is 4 marks. So we need one more set of 2. And the next part is that while technology can remove outliers. And while the mark scheme doesn't say appropriate, sometimes you just genuinely have a piece of data which might seem like an outlier, but it's not actually an outlier. For example, if you're looking at people's heights and there's this really lanky guy, you're not going to just take him out of all your data because it is lanky and it doesn't fit your pattern. He's a genuine lanky guy and you have to make him feel included. So you have to keep some outliers which make sense. Only the appropriate ones that shouldn't be in the data, you remove those. And technology is good at doing that. And what is an advantage of removing outliers? Well, this makes the data unbiased. So that's kind of 6 marks. I'll kind of highlight or show how many marks. So from these two, basically where it's splitted with the comma, you'd get a mark each. So it should be 2 marks from this part, 2 marks from this part, and 2 marks from this part. There are some more other things that you could think about. For example, ordering the data by the ages or the number of appointments. You can also remove extraneous data, which is just irrelevant data, by the way. I forgot to mention that. Irrelevant data is another word for extraneous data. You can identify missing data. You can automate the production and calculation of summary statistics. And on the other hand of this, what else can it do? It can reduce errors in the calculations, and it makes data more visually appealing. Though I wouldn't really go with that, and I wouldn't have thought of that anyways, that last one. Number 6. A large number of runners took part in a 5-kilometer race. Here are some of the results for the runners. Here are the runners A to G and their race times. Maya wants to represent the results of all the runners using a stem and leaf diagram. Discuss 2 things Maya must do to be able to represent it in a stem and leaf diagram. So you're going to need prior knowledge of stem and leaf diagrams here. So I'm just going to work through the basics and we're going to go through the absolute basics. Now, we're going to need a key. Now, key just basically decodes how you read the thing. And I'm just going to write this. So this would equal to 24. And you can see how it kind of makes sense where the tens columns are here and the ones columns are here. So I'm going to output quickly a stem and leaf diagram for you to just see, and I want you to spot the patterns and anything that you see within the stem and leaf diagram, and it will help you answer this question below. Okay, so now you see this. What are some things that you recognize from this? So if you know that 2 with a line and 4 is equal to 24, we don't need to really care about the units here. They will be given in the question or when you need to make one. But for now, we're just looking at the absolute basics. 2 with a line and 4 equals 24. So you can see for the top line of here, this will equal to 10 and 12, then 21 and 21 for the next one, and then 33 and 39, etc., etc. What you can see that these are integers and they're in the same format. They're not, for example, if you look at this, we've got runner A has 16 minutes and 24 seconds, and this one is 22:31, which I'd assume to be 22 minutes and 31 seconds. They're the same thing, but they're written differently, whereas in the stem and leaf diagram, they need to be the exact same thing, either a number or something similar. And that's basically one issue we're seeing, that we can't represent this in a stem and leaf diagram straight off the bat, because how are you meant to write 16 minutes and 24 seconds in a stem and leaf diagram without formatting it first? And so that's our first point, is that the data must be formatted, or a better word to use is cleaned. Now in this context, it could mean here, you can see this specific value for f is 30,57. It's just a misread or a mistype or whatever. So you just want to remove the comma and replace it with something else, or a colon, or whatever you format it into. And again, for A and E, you might want to remove the words and therefore make it into a nice integer format. That's what cleaning means. And it could also mean rounding it and rounding it to the same units perhaps. And that's another thing we must need to come to. If you look back at the stem and leaf diagram, what can you notice about everything here? So you look at all the data from 1 to 4, that's ordered, and if you look at all the data in terms of horizontal, it's going 10, 12, 21 and 21, 33 and 39, 40, 46 and 47. And they all go in chronological order, or they are ordered. So the data must be ordered. And there's 2 marks. Now I did touch on this earlier. Another point on the mark scheme is to round it to the same units. For example, here we can see integer. Now there could be some ways you might want to write it, for example, but here 19.2 minutes, well, that's not exactly the same as 16 minutes and 24 seconds. It would be more like 19 minutes and 12 seconds. And you can see it's 2 marks, so each one gets 1 mark each. Now for part B, we need to explain whether or not it will be appropriate to represent the results of all the runners using a scatter diagram, a histogram, and a time series graph. 3 different graphs that you need to know. It's not really too much to know, and you should just know these off by heart anyways. And one thing to know is a scatter diagram is simply a graph like this, and you have a variable on the x-axis, a variable on the y-axis, so there's 2 variables, and we call this bivariate data. Now let's go back to our table and inspect. Do we have bivariate data? It seems on the surface level we do. We have a runner and we have the race times. 2 variables, so far so good. It has our x and our y variables, which fits the need for bivariate data. But then you need to look at it in a bit more detail. What does runners actually represent? Well, this represents A to G, or the actual runners themselves. There's no numbers or anything attached to them. You could just replace these with names and it'd easily be the same thing. The race time, sure, you can actually plot these, because you can plot these along the x or along the y because they're quantifiable, whereas runners aren't quantifiable. Sure, you might plot A here, then B here, then A, B, C, D, like so, but that's not quantifiable. So you're not really seeing the relationship between 2 variables. You're just seeing at runner A, they do this, runner B does this, etc., etc. You're not seeing a relationship because A and B are not related as the race times are. So it wouldn't be appropriate to use this. Now a histogram on the other hand is a bit different. It's also another 2D graph, but on the side you have frequency, and on the bottom you have your class intervals or your class widths. Now what are your class intervals or your class widths? Well, an example for here would be, well, if we look at our minimum, we have 16 minutes and our maximum seems to be 30 minutes, so we could have 15 to 20, 20 to 25, and so on. Now the point here is that this is continuous data. Continuous data is data that can take any value in a certain range, rather than discrete data, which is countable values. Now, as opposed to A, B, C, and D, E, blah 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 being shown within the data, is kind of embedded in the histogram itself, like so. It's hard to explain in that sense because the data is just automatically included. The bars themselves represent how many. So if there were A and B were both inside, I don't know, let's say this range, then this bar obviously represents it because it's got a higher frequency rather than showing A and B specifically. Now the question is it appropriate for a scatter diagram needed to be bivariate data, whereas a histogram needs to have continuous data, as I mentioned earlier? And does this have continuous data? Well, time is continuous, and that is true, therefore we can say it is appropriate because it is continuous data. And the last one, a time series graph. Yet another one that you need to know. On the x-axis you have time, I wonder where that comes from, and then on the y-axis you need frequency. The idea is as the time moves on you plot different frequencies here, here and here, and then you join them up like so. Now, can we do that here? A large number of runners took part in a 5 kilometers race, and from here he doesn't tell us, but I'm going to assume that they've done it in the same day. So I'm going to put that it is not appropriate as all data was taken in the same day. Another thing I want to mention is that it says that they take a race, and you do a race typically with each other at the same time. So even if you want to make the argument that the hours within the days, well, no, because they do it at the exact same time. It's just the same day is what it says in the mark scheme. Question 7. You should hopefully get by now that as you go through the paper, you'll see topics that you're not familiar with, and please go and revise those. And obviously, with the ones that you're confident on, just make sure to do some more questions. The table gives the simple index numbers with 2013 as the base year for the average prices of houses in Scotland and in Wales for the years 2014 to 2017. The table also gives the chain-based index numbers for the same information, and here's all the data, given an interpretation of the simple index number 103.6 for Scotland. So if we look at that on the table, that is this value here, simple index number in Scotland. Now what does this mean? So now I'm going to introduce you to simple index numbers. An index number itself is where you compare something to the base year. Now a base year just means the year you want to start with. So right now it doesn't need to actually utilize this information, but you need to know that the base year is always given a value of 100. So base is equal to, well, the base value or the base year is equal to 100. So every other value is relative to the base value. So 103.6 is relative to 100, and we're told our base year is 2013. So if 2013 is the base year and 2014 is obviously a different value, then we're just going to see that whatever the difference is from index numbers from 103.6 to 100 is the difference for 2014 compared to 2013. So we can write this, and we can see comparing 103.6 to 100, you can see there's a difference of 3.6. Now another thing I need to show is that the difference multiplied by 100, so you can kind of imagine this is a is 103.6%. So the difference between these two gives us our percentage. So there's a 3.6% increase in house prices between 2013 and 2014. David bought his house in Wales for £165,000 in 2013, using an appropriate index number to calculate an estimate for the price of his house in 2017. Let's highlight the key information. Here, Wales, the actual price, and we know that it's in 2013. 2013 is important here because that is the base year. What else do we know? Well, we want to find the estimate of the price of his house in 2017. So we're going to find 2017 on the table, so the 2017 column, and then we want to make sure that we're mapping it to Wales, which is in these last two rows. And then we want to, since we're still on simple index numbers, the whole thing is on simple index numbers, we're going to use this value here, 115. Also known as a 15% increase. However, how do you write that as a multiplier? So if it's a 15% increase, and let's just attribute that to the 115 index number, they can also write a 15% increase as 1.15 as your multiplier. And so now the new price is going to be 15% greater than 165,000, or 165,000 multiplied by 1.15. I'm just going to type this into the calculator. And I get this value here, 189,750. Part 2 tells us to comment on the reliability of the estimate, and that's a key word there. So let's go back to the question. The table gives us simple index numbers for the average prices of houses in Scotland and Wales, and therefore the simple index numbers will be based on the average price increase or decrease, but here's increase. So if we're looking at the reliability of this estimate, well, just because the average house prices went up, David's house might have gone up higher, lower, it might have even decreased, or it might be the exact same. However, we don't actually know this, so what we can write is that the actual index numbers themselves represent the average increase in house prices. We can also write, however, the actual price of the house for his specific one may vary. Part C now, and we've come to our first proper large calculation question, and it's worth 5 marks. By finding appropriate geometric means, compare and interpret the yearly average change in house prices from 2013 to 2017 in Scotland and in Wales. I'm going ahead and I'm going to highlight the key information. Geometric means, compare and interpret the yearly average change in house prices between 2013 and 2017 in Scotland and in Wales. So yeah, the two sentences pack a punch and it has a lot of info that we need to digest. The first thing we need to look is at Scotland and Wales. So we're going to be looking at the table here and we're going to be identifying Scotland and Wales. Now we've done this, we need to find the appropriate geometric means. Now before I explain what a geometric mean is, we need to find which one this is for. So now we need to focus on another part of key information, the yearly average change in house prices. Now, whereas the first question or the first part was the simple index number, which represents the change from the base year, here it's showing the yearly average change in house prices, which indicates we're using the year before the last. So if you're using 2015, the previous year would be 2014, and if we move to 2016, the previous year would be 2015. So which one do we use? And here's another piece of information, is that the chain-based index number in this scenario, or in every scenario, is where you use the previous index number in your calculation. So these ones are the ones that we're interested in. In this context, the chain-based index number represents the direct increase in house prices from the previous year. So if we take this value, 101.5, this is a 1.5 percent increase compared to 2015, rather than obviously the simple index number where it's directly compared to 2014. So now we've got this information, we can actually start going about our calculations. And now we need to find the geometric mean. Now the geometric mean takes a formula, and that is as followings. Now, the formula is the nth root of each value in your sample set, or whatever you want to say, up to the nth term or the nth value, and then you just take the nth root of it when you multiply them all together. I won't go into too much detail here because this is something that you will need to cover, and if you don't know what I'm on about, you just need to go and learn it and revise it. However, it's kind of a different type of mean compared to the arithmetic mean. Anyways, we're going to use this formula and we're going to plug it in for our Scotland and Wales house price increases. So we'll start with Scotland. Okay, so if we look at Scotland, and that is everything in this row here, so let's just highlight it. We're looking at all of these. So basically we're just going to multiply each of these and take the nth root of it. And the n here is 4 because there are 4 years. So I'll go ahead and I'll write this all out. And I'll go ahead and I'll type this into my calculator. And I end up with this value, 103.23172 blah blah blah, and this is the equivalent of 3.2317 and so on percent increase. I'll round it to 3 significant figures, so I'll do 3.23% increase. Now I'll do the same for Wales. I have to apply the same formula, so it will again be the fourth root, and let's go to the table and we're going to look at all of these. I'll then multiply them together, take the fourth root, as yet again there are 4 values for 4 different years. And I'll type this into the calculator now. This gives me 103.54707 and so on. And if I take this as a percentage increase, this is the 3.547 and so on increase compared to the previous years on average. And so this to 3 significant figures is 3.55%. And I'll indicate that here. So 3.23% increase. So for Scotland, I'll write that 3.23% is the yearly average rate of increase. And I'll do the same here for Wales, and for Wales 3.5% is the yearly rate or the yearly average rate of increase. Okay, so now I found the geometric means, and I've also found and I've done it for Scotland and Wales. Now we need to go to the compare and interpret. So we need to compare these. The values we've got are 3.23 and 3.55. So we need to compare it. Now the easiest thing to do is just compare which one is bigger, and that is Wales. So Wales, which has a 3.55% average yearly increase, is greater than Scotland, with a 3.23% increase. Now, what does this suggest? That the yearly average rate of increases in Wales was greater than in Scotland. So I'll write that down now. Now that was a not difficult but a tedious question. It was 5 marks, so it was kind of worth it. I'd say it's a good question overall. You just need to know the formula for the geometric mean. You need to identify that it's for chain-based index numbers, plug it in, find the values, compare and interpret. And it's basically packed into these 2 sentences. If you can break it down properly, then you'll have no problem getting all 5 marks. Question 8. Stacy is the manager of a large company. She wants to investigate the differences between the number of days of holiday taken by employees in different age groups. She obtains the following information about the ages of the employees. And here's the data, and we need to assess the suitability, taking a sample of 20 employees stratified by age and by gender for her investigation. Again, we'll just highlight the key information. She's taken a sample of 20 employees, and she's actually stratifying them. I have a video on stratified sampling, so if you don't know what it's about, I'd recommend watching it. In a nutshell, it's just proportionate sampling of the population in your samples or your subgroup. So, what is the suitability of 20 employees stratified? Well, we can kind of see that there are a large number of employees here in total, somewhere roughly around the 300 mark, around that part. So if you're taking a sample of 20, the sample size is a bit too small, so we can write that as the point. But if we're looking at it from a different perspective, we could actually say that this is suitable. And why is that? Well, this actually fairly represents all of the groups, and so we can say that it's representative of the population. So and because of that, we could also say that it reduces bias. And another thing you need to know is that when you stratify a sample, you use random sampling to actually gain that sample. So it will reduce bias because you're not actually subconsciously picking one person over another, you're doing it randomly. So we can also use that as another point. Now if you like, you might want to add a connector just to make it smooth flowing. So you can see that there's 1 mark from the top and 2 marks from the bottom. If I check the mark scheme, what else does it say? You could say that it's not appropriate because you shouldn't stratify by the variable you're investigating, and here that is age, which is true. And it would be better if they stuck to 1, for example, just gender. Question 9. The table gives information about the scores achieved by students in a French test and in a German test. The scores in each test are modeled by a normal distribution. Here's the data, and on the grid we need to sketch a diagram for each of the distribution of scores and label each of them. So let's just highlight what we know. A normal distribution is something you must be familiar with, not in too much detail, however you still need to know the key characteristics. And then we just need to sketch, which means you don't have to be plain accurate, but it needs to have the general gist. Therefore you need to be able to show some differences between the two. So let's quickly look at the key characteristics of a normal distribution. So if we just have this here, we have this sign is marked as the mean, and this is the peak of a bell-shaped curve, and that is one key feature, is that it is bell-shaped. And then you need to also learn that there are different levels of standard deviations. You can have 1 standard deviation, 2 standard deviations, and 3 standard deviations, and all of them come with a plus or minus, and that indicates that it is plus or minus from the mean. So you could have the mean plus or minus 1, 2, or 3 standard deviations. And then there's the empirical rule with the 67 or 68 formula. You just need to look at that and revise that. However, right now you don't really need to think about it too much in detail. We're given the standard deviation and the means, so we can start by looking at just the French. The French has a mean score of 78, and it's got a standard deviation of 2. Now, pretty much 99% of the data, or somewhere thereabouts, data is within 3 standard deviations each side of the mean. So anything outside 3 standard deviations we don't really care about too much, and it's not really highlighted. So what we can really show is basically a bell-shaped curve, the mean, and the standard deviations, and they're giving us this data here conveniently. So we need to mark out 78 on the diagram here, and we'll do that here. So 77, which is here. That's going to be our peak. Now we need to look at our tails. Now, each bell-shaped curve has a tail, and for the lower tail we're going to have to look 3 standard deviations to the left. Now that would be 78, subtract 3 lots of the standard deviation, and we're given the standard deviation is 2, which is equal to 72. So that's going to be roughly where we're going to try and aim for, and around here. And then I'd want to mark out the upper tail, which would be 78 plus 3 standard deviations, which would give us 84. So we're going to mark that here. And then now you just draw a rough bell-shaped curve, and you'd want to touch or thereabouts a peak at 78, like so. That's just a sketch. There isn't much more that you need to do. And then it says label each diagram. This is for French. Now this is going to be 72, this is going to be 84. This is your 3 standard deviations, and you're basically encapsulating the 1 and 2 standard deviations within, so you don't need to sketch that bit. You could illustrate it, but we don't have to do that here. And now we need to look at German. Now German has a higher mean score, 85, compared to the 78, but its standard deviation is higher as well. The standard deviation measures the spread of the data, and it's a good way of measuring how diverse a data set is. Now, if the data is more spread out, it will have a higher standard deviation. Okay, so you might need another piece of information, which is that the area under the curve is pretty much the same. It represents probabilities, and these add up to 1. So the idea is the 2 curves need to have the same area, but the areas are going to be represented differently. Now, because the mean score is 85, it's going to be on this line here, but we need to know where we're going to plot it. We can't exactly plot it exactly in the same peak, because as we can see, the standard deviation is different. The spread of data means that there's more variation in the data set. Hence, we might actually have to reduce the peak of the mean. So we're going to do it somewhere lower, approximately anywhere here would look nice. And then now we can just use our lower tailed and upper tailed and do the mean plus or minus 3 standard deviations. Now if you put those values into the calculator, 85 plus or minus 3 lots of 2.5, you would get 77.5 and 92.5. I'll start sketching them now. Now you'd want to sketch some sort of curve here, just like the other one. Obviously they do not look nice, but again, it's just a sketch. As long as you've shown the bell-shaped curve, you've marked down the approximate tails at the values using the 3 standard deviations, and you made the peak of the Germans lower because it shows there's more spread of data, then you should get the 4 marks. Part B, use the information in the table to make two comparisons between the scores in the French test and the scores in the German test, and then interpret your comparisons in context. So first of all, we need to make two comparisons, and we just need to use the data, and then we need to interpret those comparisons in context. So when we're doing this, we basically just need to look at what the table's given us, and it's given the mean and the standard deviation. Now the mean generally indicates that German tests, had a higher average score than the French, and its highest standard deviation suggests that it's more spread out. That's basically the answer. I'll write that down now. Quick pause, I'm just going to clarify what I've written here. I've written that the test results are generally greater because of the higher mean, and now I'm going to write that the test scores for German are more spread out, and we can see this because of the higher standard deviation, and that's what it means by interpreting the actual comparison, and that's the more spread out and the generally greater scores. One student who took the French test is selected at random. Work out an estimate for the probability that this student scored more than 76 on the French test. So I'm going to have to introduce you to the empirical. Now the empirical essentially states all the data must be between 68, 95, or 99.7%, or 99.7% of the data lies within the specific standard deviation. This is for 1 standard deviation, 2 standard deviations, and 3 standard deviations of the data. And you can illustrate this like so. You have your mean here, and then you have 1 standard deviation each side, 2 standard deviations each side, and then 3 standard deviations each side. Obviously this isn't an accurate diagram, but the idea is you cover more and more data with each standard deviation, and the exact values are here. Now you might see slight variations online like 67, and sometimes they might have different values. This is the general one you can use. Just use the one that you see in your notes or in the textbook. So what this relies on is seeing that, well, for the French we had the mean score was 78 and the standard deviation was 2. If you can manipulate those numbers to get 76, you can kind of see that 78 minus 2 gives us 76. Now if 2 is the standard deviation and this is the mean, well, you can kind of look at it. This is the mean minus 1 standard deviation, and if you look at this being the mean, and we're looking kind of at this bit here, everything within this little bar is the mean minus the standard deviation, or 1 standard deviation. Now it's saying to work out an estimate. Again, this will be an estimate. We don't know for sure that this student scored more than 76. Now that's key. If we look at our actual diagram here, where it might be better to illustrate. So for French, it illustrates 78. 76 is here. So if I quickly just draw these dashed lines, this is the mean minus 1 standard deviation. Now we're trying to find the probability it was greater than or equal, or not greater than or equal to, but greater than 76. So therefore we're trying to find everything that is in the pink plus everything that is in the yellow and ignore the overlap. Another key thing that you need to know is that this is kind of split in half. The mean basically represents the middle part of the data, which is a key characteristic of the normal distribution. So 50% of the data lies here and 50% of the data lies on the other side. So if you look at that key characteristic, you can kind of see that, well, this bit must be 34% and 34%, because if you think about it, this is 1 standard deviation in total, plus or minus the mean, which gives us our 68. So the probability that the student scored more than 76 is everything to the left of the mean, which is 78, and that's 50%, and everything between 76 and 78, which we've identified as one standard deviation below the mean. Now we know that one standard deviation plus or minus is equal to 68% as per the empirical rule, but because we're just looking at the negative part, we're going to have to divide by 2, which gives us 34%. So therefore the probability is greater than 76 would be equal to 0.34 plus 0.5, which gives us a probability of 0.84 or 84%. Lucy took both the French test and the German test. Before she took these tests, she said that the probability that she will score more than the mean score in both tests is a half multiplied by a half, which is equal to a quarter. Comment on the validity of what Lucy says. If you think back to question 1 before we checked, and independent events. Independent events means that the probability of doing one thing or one event is independent, i.e. it's not affected by doing something else. Now here she's assuming that because 1/2 multiplied by 1/2 gives us our quarter, well, this assumes that it's independent. Now, is it likely to be independent? Well, just think about it for a minute. If you're doing a French test and a German test, well, they're naturally linked together, they're languages. If you're going to do a French test and then a German test, you're probably going to be smart because no one's going to do that by force. So she's likely to score higher on both tests, and this is because she takes 2 languages. So what I would say is that it's unlikely to be valid because it assumes independency. Question 10. A company makes bars of chocolate on a production line in a factory. If a chocolate bar is found to weigh less than 60 grams, the company will not be allowed to sell it. The company uses quality assurance control charts to monitor the weight of chocolate bars. Samples of chocolate bars are taken at regular intervals, and the mean weights of the samples are normally distributed. Explain why it would not be appropriate for the production line to be set so that 60 grams is the target weight. So quite literally, if 60 grams is the target weight and it is normally distributed, so again we're going to introduce our bell-shaped curve. 60 grams is the target, 60 grams the target is always the mean. So the mean is going to be what you're targeting. Now if you target 60 grams as your mean, well, anything less than 60 grams, well, what happens? It's not allowed to be sold. We'll not be allowed to sell it. So would you want to do that? Probably not. So that's the reason you're going to put. If you don't already know by now, 50% of the data is to the left and the right of the mean respectively, because the mean is obviously the median, isn't it? In fact, the production line is set so that the sample mean should be normally distributed with a mean of 62 grams and a standard deviation of 0.4 grams. What can be deduced from this information about the mean and standard deviation of all the chocolate bars made on the production line? So all the chocolate bars made on the production line, I need to refer to this as the population, and the population is again everything you're interested in, and this is all the bars on the production line. And then you've obviously got your sample, which is, well, the subset of data which you select. Now what can we deduce about each of the mean and the standard deviation? 2 marks and 2 rough points that we're going to base it around. So for the mean, look at the 62 grams. What should we deduce from this? Well, you can kind of see that the mean of the population should equal to, or roughly equal to 62 grams, as that's what the normal distribution follows, a mean of 62 grams. So we can deduce from this that the mean of the population should be roughly equal to the mean of the sample, which is 62 grams. So the mark scheme does word it a little bit weirdly, I'll admit, but it kind of makes sense. You're going to try and aim for the mean of 62 grams, but obviously you're not going to hit 62 grams exactly, you're going to have slight variation, hence the standard deviation. Speaking of which, I need to highlight this keyword here, sample means. Now, sample means is when you have a population, and from that population, you take a random subset of data, which is your sample, and you take the average. You do this multiple times to obtain another dataset, which is full of the means of your different samples, and obviously that's where sample means comes from. So the idea of a sample mean is that it's going to be less, but it still will be, but to a lesser extent, it will be less affected by outliers and such, and therefore the standard deviation of the population, which is basically your raw data, will be greater than the standard deviation of your sample means, which of course will now be more closer together because they've been averaged, and that's your second point. Alice takes the samples in order to monitor the sample means of the weights. Here is her incomplete control chart showing 8 sample means. Part C tells us, by completing the control chart, determine what actions, if any, Alice should have taken based on the information given. You must justify your answer. Okay, so the only incomplete information here is that it seems all the sample numbers have been given to us. Sometimes they like to ask us to fill one in and plot it on the graph. However, we don't have to do that here. However, quality assurance isn't particularly difficult. You just need to know some specific things. Now, there's something called action lines and warning lines. It's quite self-explanatory. The action line is when you're actually going to do something, when you're going to act on something, and a warning is perhaps when you're just about to act on something but not quite yet. And this happens at particularly plus or minus 2 standard deviations and plus or minus 3 standard deviations. Now the idea is, if any of the data falls outside 2 standard deviations, then we're going to give a warning. Now, if it falls outside the action limits, the upper and lower limits, then we will actually take action, and in most cases it's stopping the production line. So first of all, let's look at the standard deviation. Standard deviation given to us is 0.4 grams. The mean is given to us as 62. Now we always look at the warning limits first, or I do anyways, so we're going to do plus or minus 2 lots of the standard deviation. For our lower limits, so 62 minus 2 lots of 0.4, we get 61.2. And for our upper limits, so where you have to add 2 lots of 0.4, we get 62.8. Okay, so now if we look at this, we need to plot this on the graph. So our values are 61.2 and 62.8, so I'll just spend my time plotting them now. That was quite fiddly, however, you should be able to do it with a bit more accuracy. So this would be our upper warning limit, and then our lower warning limit. Now you can see some data already falls outside, so now let's move on to our action limits. We'll need to do 62 plus or minus 3 lots of our standard deviation. So if we type it into the calculator, 62 plus 3 lots of 0.4, or let's do subtract first because we're trying to do our lower limits. We get 60.8. Then if we add, we get 63.2. So now we need to plot those lines, 60.8 and 63.2. So now we need to label these ones, and this will be our upper action limit and the lower action limit. So now, do we need to take any action? Well, we can see that this sample here, sample 7, is outside our warning line, but not outside the action line. And then this sample here, sample 8, is completely out of both the warning and the action line. So we have two samples we need to deal with here, and we need to do them in order, I'd say, makes the most sense. So for sample 7, you should know that when it falls outside the warning limits, but not the action limits, you'd have to take another sample. You'd usually review that and see if it falls outside the warning or action limits. And then for sample 8, well, it's completely above the upper action limit, which is unacceptable, so we just have to stop and reset the machine, which is generally what you mostly do for all the exam questions that you come across. So you get 1 mark from basically labeling your limits, and then another mark from identifying the actual values. So from labeling that you have your plus and minus 2 standard deviations and 3 standard deviations, you get 1 mark, and from actually drawing on the graph, you get another 2 marks. So, and then you'd have to actually state that sample 7 is outside the warning lines. So and then for sample 8, well, it's outside the action. And so your last marks are from here. And that is the whole of question 10. A farmer recorded the birth weights in kilograms of a sample of 50 piglets born on his farm. The grouped frequency table gives information about his results. So we'll have our weights here in our class intervals of 1, and actually no, they vary, and our frequencies on the other column. Using the information in the table and the values of W as the class midpoints, the farmer finds an estimate for the mean birth weight of these piglets is 2.29 kilograms. He also finds that the sum of the frequency multiplied by the midpoints squared is equal to 286.875. Show an estimate of the standard deviation of the birth weights of these 50 piglets is 0.7 kilograms, correct to 1 decimal place. Now, standard deviation in general, the sum of x squared over n minus the mean, which is ex over n squared, or sigma x over n squared. Now, for frequency or grouped frequency tables, it's slightly different, and you don't get given this formula. However, you do get given this formula here for the normal standard deviation, so you're not completely in the dark, and you can just learn that it's going to be the frequency just gets slotted next to the x. So the frequency multiplied by x squared over n minus the sum of the frequencies times x over n, and then square that. And they've kindly given this value here with 2.29, and they've given us sum of f of x squared, which is this one right here, and it's 286.875. We know that n is the number of values and that there are 50 piglets, so that's quite self-explanatory. So from here, it's just a matter of plug and go. So I'm just going to substitute the values in. The sum of fx squared, or fw squared as it is in the question, is 286.875 over n, which is 50. And we don't have to do the mean, thankfully, so less workings for us. So just 2.29 squared. If you type this into your calculator, you get 0.7024 and so on kilograms, and then to one decimal place we just have to round this and we get 0.7 kilograms, and that's your answer right there. So this one wasn't actually as hard as it looked. You just had to know the formula, which again is kind of given to you in the formula booklet. You just need to remember, you need to put the frequency next to the x, and then from there it's just picking out the information and plugging it in, and not too much difficulty here, but then it was only 2 marks. Calculate an estimate for the skew of the birth weights of the piglets. Go to your formula booklet and you'll know that the skew is equal to 3 lots of the mean minus the median divided by the mode, standard deviation, sorry. Look to our question here where we're given all of our data. We've got the mean here, we've got the standard deviation now to one decimal place. What do we not have? Well, we haven't got the median, so we're going to have to find that now. Now the median has a formula, and I can put it here. It's basically the start of the class width plus the remainder or something like that. I can't tell you the definition or the official formula because I haven't got it on me. You can learn this if you want. However, a more easier way to do it is just using intuition. The only way you'll be able to do this in the pressure is when you need to understand what it's actually asking for. Now, the median is just the middle point of the data. The sum of the frequencies is 50, and if you look for the median will be 50 over 2, or the 25th value. That's what it's asking us for. Where is the 25th value? Now, if you did a cumulative frequency, you'd kind of see that we have 4 here, 16 here, and then if you add 17, you'd have 33. So the 25 is somewhere within this category, the 2 and 25. Now the question is, how far into it is it? And because we're going to estimate the median, what value could we give it? So if we go back to this, it starts at the interval 2, because that's the minimum value in that interval. In terms of the class intervals, the cumulative frequency was 17 and then 33. We needed to work out where 25 went in. Now 25 is an addition of 9 out of a class width of 16, if I'm correct. Was it 16? No, it was 17. I've got the values the wrong way round. So we need to add 9 out of 17, and we need to multiply it by how large the class interval is, which is 0.5. And this gives us a value of 2.2647 and so on, and we'll just round it to 2.26, which is 3 significant figures. Now we just need to plug the values in. So the skew is equal to 3 lots of the mean, 2.29, minus the median, over the standard deviation, which is equal to, if you type this into the calculator, 0.1285 and so on, which are round to 0.13. Now they give a range for this, which is why I wouldn't worry about what you round your median to, but it's 0.1 to 0.13 if you're wondering in the mark scheme. If you're a bit confused by the median, well, I wasn't able to quite so much explain it in detail, and I probably wouldn't. I don't think it was a good explanation anyways. However, be sure to revise that. In a nutshell, this is your class interval, the minimum. We're looking how far you went into that class interval in terms of the frequencies in order to get to the median, and then we multiplied it by the class width. I know that wasn't a good explanation, but hopefully it still makes sense if you do know how to do it. If you don't know how to do it, please revise it and then come back, and then hopefully it should make sense. Part C asks us to interpret our answer to Part B. The key word is interpret. it wants you to find the value or explain it, and then you need to give context. So 0.13 indicates a slight positive skew. Now if I illustrate this using a positive skew diagram, which should look something like so, if the median was located here, then you can see that more data is packed in this part here, but there's more spread to the right of the mean. So we could say that the weights above the median have a greater spread than below the median, as you can see illustrated by the graph. Part D. Using only the information given in this question, explain whether it is possible to deduce that any of the birth weights are outliers. Justify your answer. Now, outlier limits are anything plus or minus 3 standard deviations. Now, if we look at this, we need to do the mean, which is 2.29 as given per the question, and then we need to plus and minus the standard deviation, which we find to be 3 lots of 0.7. Put this into your calculator and you'll get two values. You'll get 0.2 and 4.4, which are rounded values. Now we need to look at these values in detail. So we have 0.2 and 4.4, so remember those. Now the smallest value starts at 0.5. It's impossible to have any values less than 0.5, hence we can't have a value 0.2 because, well, there's no class interval for it. So that's impossible. Now 4.4. 4.4 could well be in here. It's possible, but we don't know exactly. Because for all we know, all the data could be 4, 4.1, 4.2, and none of them actually eclipse 4.4. However, we could also tell that some of the data could be 5.8, 5.9, which in this case would be an outlier. So all we can say is we don't know for sure, but it's possible there are outliers. And that is the end of the paper. So please do give me feedback on how I've been. I do appreciate critical feedback as well, so if there's anything that you want me to change, please be honest, and I'd rather make changes than keep the same format and just do it terribly. And also, if you appreciate it, let me know as well in the comments, because it keeps me going and motivated. And if you want a paper too, do let me know. And yeah, thanks for watching.